What if I told you that the entire digital world, every photo you've ever taken, every message you've ever sent, every single transaction that powers our global economy is built on a foundational assumption that might not be a law of nature, but merely a 70-year-old habit? For as long as any of us have been alive, we've been told that computers speak a single, unchangeable language, the language of binary, zeros and ones, on and off, yes or no. It's the silent pulse beating beneath every screen, the invisible architecture of our modern lives. It's so fundamental that we never even think to question it. It feels less like a choice and more like a law of physics. But what if it wasn't? What if, in the grand story of technology, we took the first path we found and never bothered to look for another? What if computers didn't have to be limited to just two states? What if they could have a third? This isn't science fiction. This is the story of ternary computing, a forgotten dream, born in an unlikely place, that is suddenly roaring back to life. It's a story about a radical idea that could unlock a new era of computational efficiency, one so powerful that our current binary systems might one day look as primitive as a steam engine in the age of space travel. This is the story of the ghost in the machine, and its time may have finally come. To truly grasp the magnitude of this idea, you have to first appreciate the sheer, monolithic dominance of binary. For over 7 decades, every single computer, from the room-sized behemoths of the 1940s to the supercomputer in your pocket, has been built on this simple, dualistic principle. It's the bedrock, the alphabet, the Genesis chapter of the digital Bible. Think about it. A 1 represents a high voltage, a current flowing, a switch being on. A 0 represents a low voltage, no current, the switch being off. From these two simple states, we have constructed a civilization of almost unimaginable complexity. We've built artificial intelligence, mapped the human genome, and sent probes to the edge of the solar system, all by flicking trillions of microscopic switches on and off, over and over again. It's a testament to human ingenuity. But it also reveals a collective blind spot. We became so good at building things with this 2-piece Lego set that we forgot to ask if there were other pieces in the box. We optimized the binary system to its absolute limits, making transistors infinitesimally small, cramming billions of them onto a single chip. But we never stepped back and asked the most fundamental question of all: was binary the best way, or just the first way that worked? This is where our story begins, because questioning that foundation isn't just a technical exercise, it's a philosophical one. It's the difference between seeing the world in black and white, and suddenly realizing that the universe is bursting with color. The bold idea of ternary computing proposes that our digital world doesn't have to be a flat, two-dimensional landscape. It could have depth. It could have a third state, a middle ground, a new dimension of information. And in that third state lies the potential for an efficiency so profound, it could solve some of the biggest problems we face today. To find the origin of this revolutionary idea, we have to travel back in time, to a place where innovation wasn't driven by corporate profit margins, but by raw necessity. Picture the Soviet Union in the 1950s. The Cold War is in full swing. In America, giants like IBM are beginning to mass-produce powerful, sophisticated computers, laying the groundwork for a technological empire. These machines are polished, reliable, and backed by immense industrial might. Meanwhile, behind the Iron Curtain, the situation couldn't be more different. The USSR is technologically powerful, yes, but its approach to computing is almost artisanal. Their machines are complex, incredibly expensive, and often built by hand, piece by piece. They are technological marvels, but they are also fragile beasts, confined to top-secret military labs and elite state institutions. The idea of a computer for a university, on loan for a student, was almost unthinkable. It was in this environment of scarcity and constraint that a brilliant young engineer named Nikolai Brusensov, working at Moscow State University, began to dream. He looked at the colossal, power-hungry binary machines of his time, and saw not just a technical challenge, but a philosophical one. He saw a system that was needlessly complex and expensive. He believed that computers shouldn't be a precious artifact locked away in a vault. It should be a tool for learning, for discovery, accessible to the next generation of scientists and thinkers. Brusensov and his small, dedicated team didn't have the resources of IBM. They couldn't order thousands of pristine, mass-produced components. They had to make do with what they could find, often building their dreams from what amounted to electronic scraps. But, as is so often the case in history, it was this very scarcity that forced them to think differently. They couldn't just build a cheaper version of an American computer. They had to build a smarter one. They had to rethink everything, right down to the most basic principles of how a machine could think. Their dream was radical, simpler, cheaper, or elegant computer for the people. And to build it, they would have to leave the binary world behind. Every great invention has its eureka moment, a flash of insight that changes everything. For Nikolai Brusensov, that moment didn't come from a schematic or a transistor. It came from a conversation. He was introduced to a renowned mathematician named Sergei Sobolov, one of the intellectual titans of the Soviet era. As they discussed the challenges of building a more efficient computer, Sobolov casually mentioned an old, somewhat obscure branch of mathematics, ternary logic. For Brusensov, this was the key that unlocked the entire puzzle. For centuries, Western logic, stemming from Aristotle, was built on the law of the excluded middle. A statement is either true or false. There is no in-between. Binary code is the perfect digital expression of this. 1 or 0, true or false. But ternary logic operates on a different principle. It allows for 3 states. Instead of just true and false, it introduces a third option, unknown, or inapplicable, or undetermined. In a mathematical system, this could be represented not as 0 and 1, but as 1, 0, and 1. This is a concept known as balanced ternary, and it is stunningly elegant. The 0 sits perfectly in the middle, a neutral state, with a negative and a positive value on either side. It's symmetrical, it's intuitive. It mirrors concepts we see in the physical world all the time: negative and positive charges, with a neutral ground in between, forward, reverse, and neutral in a gear shift. For Brusensov, hearing about this was, as the source text beautifully puts it, like discovering color in a black and white world. Suddenly, he saw a path forward. The binary world, with its endless chains of zeros and ones, seemed clunky and inefficient in comparison. Why use 2 binary bits to represent 3 states, when you could use just 1 ternary digit, a trit? He and Sobolov immediately saw the potential. A computer built on this balanced ternary system could have simpler circuits. The mathematics of computation itself would become more direct, more streamlined. For example, in ternary logic, you don't need a separate sign bit to indicate if a number is positive or negative. The sign is inherently part of the number itself. 1. This reduces complexity at a fundamental level. It was a mathematical revelation that promised to translate directly into a physical one, a machine that was not only cheaper to build, but more powerful in its very design. Armed with this new mathematical vision, Brusensov did something that few in his field had ever dared to do. He launched a full-scale assault on the unquestioned dogma of binary logic. He argued that the entire world had fallen into a trap of historical convenience. Binary wasn't chosen because it was the most perfect or efficient system. It was chosen because the earliest electronic components, the clunky mechanical relays and fragile vacuum tubes, were naturally binary. Think about it. A relay is a physical switch. It's either open or closed. A vacuum tube is either conducting a current or it's not. These components had 2 stable states. So, naturally, the entire architecture of computing was built around this limitation. It was the path of least resistance. And once that path was paved, once the first programming languages were written and the first hardware was designed, the momentum became unstoppable. The world, Brusensov believed, had mistaken a technological stepping stone for the final destination. He saw it as a profound failure of imagination. He and his team set out not just to build a new machine, but to prove a philosophical point. They were building a machine that literally thought differently. They embraced the balanced ternary system of 1, 0, and 1. This wasn't just an arbitrary choice. It was deeply practical. In their machine, these three states could be represented by physical phenomena: a negative magnetic polarity, 1, no magnetismo, and a positive magnetic polarity, +1. Or, with transistors, a negative voltage, 0 voltage, and a positive voltage. This defiant philosophy was embedded in the very soul of their creation. They weren't just assembling parts, they were making a statement. They were saying that the digital world didn't have to be a rigid, black and white construct. It could be more nuanced, more balanced, more efficient. Their machine, which they would name Setun, was conceived as an act of rebellion against the tyranny of two. For 2 grueling years, Brusintsov and his small team at Moscow State University worked in relative obscurity, fueled by little more than conviction and ingenuity. They tinkered, they tested, they failed, and they tried again. They were inventing an entirely new form of computing from scratch, without a roadmap or a blueprint to follow. Every circuit, every logic gate had to be reimagined for a 3-state world. Then, in 1958, Setun whirred to life. And it was a masterpiece of minimalist engineering. In an era of computational giants that filled entire rooms with thousands of vacuum tubes, Setun was remarkably compact and efficient. It was built using ferrite cores for its memory and logic, which could be magnetized in one of 3 states: positive, negative, or not at all. It used only about 2,000 of these magnetic elements and a mere 100 germanium transistors, a tiny fraction of the components used in its binary counterparts. The results were staggering. Setun was, by some estimates, 10 times cheaper to manufacture than comparable binary computers of the day. Its architecture was 30% simpler, making it more reliable and easier to maintain. It was also remarkably energy efficient, a concern that was secondary in the 1950s, but has become one of the most pressing issues in modern computing. By 1959, the project was deemed a success, and a small production run began. About 50 Setun units were built and distributed to universities, research institutions, and even some factories across the Soviet Union. For a brief, shining moment, it seemed as if Brusintsov's dream had come true. A new kind of computer, cheaper, simpler, and accessible, was making its way into the world. It was a quiet, almost hidden revolution, a groundbreaking moment in computer history that unfolded far from the spotlights of the Western tech world. The ghost in the machine had been born, and it worked beautifully. Setun was a marvel. It was efficient, it was cheap, and it was elegant. By all technical measures, it should have been the start of something big. So why have most of us never heard of it? Why are we living in a binary world, and not a ternary one? The answer is a tragic lesson in how innovation really works. A brilliant idea is not enough. A working prototype is not enough. The fate of Setun was sealed not by technical failure, but by the colossal, unyielding forces of politics, economics, and global momentum. First, there was the Soviet ecosystem. While Brusintsov had proven his concept, the Soviet Union's centralized, bureaucratic system lacked the industrial scale and agility to truly champion such a radical departure from the norm. To mass-produce ternary computers, you would need an entire industry to retool. You'd need factories dedicated to making ternary components. You'd need a new generation of programmers trained in a new way of thinking. The Soviet state, focused on massive, top-down projects, was ill-equipped to nurture this kind of bottom-up revolution. The institutional inertia was just too great. But the even bigger obstacle was the world outside the Iron Curtain. By the late 1950s and early 1960s, the West, led by the United States, had already gone all in on binary. Billions of dollars had been invested. A vast ecosystem of binary hardware, software, programming languages like Fortran and COBOL, and trained engineers had already been built. For the rest of the world to switch to ternary would have meant abandoning that colossal investment and starting over. It was like trying to convince a country that had already built a nationwide railway system to tear it all up and adopt a completely different track gauge. The world had locked itself into a path. Setun didn't fail because it didn't work. It failed because it was out of sync with the rest of the planet. It was a brilliant answer to a question that, for most of the world, had already been settled. And so, this remarkable machine and its visionary creator slowly faded into the footnotes of history, a ghost of a future that might have been. The world wasn't ready to rewrite its technological DNA. Fast forward 70 years. The world that chose binary has been transformed by it. But now, that very system is beginning to show its age. We are hitting a wall, and it's the exact same wall that Nikolai Brusintsov saw all those decades ago. A wall of inefficiency and complexity that we can no longer ignore. The signs are everywhere. The explosion of artificial intelligence is the most prominent example. Training large AI models like the ones that power ChatGPT or create stunning digital art requires an almost obscene amount of computational power. This, in turn, consumes staggering amounts of electricity. Data centers, the vast digital factories that run the modern world, are now responsible for a significant percentage of global electricity consumption, rivaling the energy usage of entire countries. Their carbon footprint is a growing environmental crisis. Our insatiable demand for more data, faster processing, and smarter algorithms is straining our power grids and our planet. We've pushed binary to its absolute physical limits. Moore's law, the observation that the number of transistors on a chip doubles roughly every 2 years, is slowing down. We can only shrink transistors so much before we run into the bizarre and unpredictable laws of quantum physics. We are reaching the point where simply adding more binary switches isn't the answer. We need a fundamentally more efficient way to compute. And so, in our moment of crisis, the ghost of Setun Ray emerges. The question that Brusintsov asked in the 1950s is being asked again, but this time with a desperate urgency. With our advanced materials science, our mastery of nanoscale engineering, and the existential pressure of climate change and exponential data growth, the world is finally ready to listen. Could three-state logic, the road not taken, be the path forward? Could Brusintsov's lost dream be our last, best hope for a sustainable digital future? For decades, ternary computing remained a curiosity, a topic for academic papers and theoretical discussions. But recently, a modern tech giant has made a discovery that might just resurrect Brusintsov's dream from the pages of history. That giant is Huawei. In a series of groundbreaking patents and research papers, engineers at Huawei have unveiled a new type of transistor design that could be the key to practical, modern ternary computing. To understand how significant this is, let's go back to our simple switch analogy. A standard binary transistor, the kind in your phone or laptop, operates on a single threshold. Think of it like a dam. If the water level, the input voltage, is below the top of the dam, the threshold, the switch is off-O. Once the water level rises above that single threshold, the switch flips to on-1. It's a simple, one-step process. What Huawei introduced is a device with two thresholds. Imagine a dam with a spillway halfway up. If the voltage is below the first, lower threshold, the state is off. Let's call that our -1 state. If the voltage rises above that first threshold, but stays below the second, higher threshold, the transistor enters a distinct middle state R0. And if the voltage pushes past that second, higher threshold, it enters the final on state R1. By engineering two separate voltage thresholds into a single transistor, they created a component that is naturally, physically ternary. This isn't a software trick or a clever workaround. It's a fundamental change in the hardware itself. This breakthrough is monumental because it means we may no longer have to build ternary logic gates by awkwardly combining multiple binary ones. We can build them directly, from the ground up. But this innovation is also a monumental challenge. You can't just drop a ternary transistor into a binary computer. It demands a complete paradigm shift. It requires us to reinvent everything: the processors, the memory chips, the logic circuits, and all the software that runs on top of them. It's a call to rebuild our digital world on a new foundation with 3 states instead of 2. Brusintsov's vision, once a theoretical curiosity, now has a potential physical form for the 21st century. The promise of a new transistor is intoxicating, but the path from a single component to a functioning computer is incredibly long and difficult. Reinventing the entire computing stack is a task of breathtaking scale. Let's break down what that really means. At the lowest level, you have the logic gates, the fundamental and NOT gates that are the building blocks of all computation. These would need to be completely redesigned for three-state logic. Then there's memory. How do you store a 1, 0, or 1 state reliably and access it quickly? That requires entirely new memory cell designs. Moving up the stack, you have the processors themselves, the CPUs and GPUs. Their entire architecture, from the instruction sets they understand to the way they perform arithmetic, would need to be rebuilt from the ground up for a ternary world. Then comes the software. Compilers, the crucial programs that translate human-readable code into machine instructions, would need to be rewritten to speak ternary. Operating systems, the very soul of the machine, would need a ternary native design. It's a Herculean effort, and yet, the potential rewards are so great that companies are pouring resources into it. Huawei's patent data, though just a glimpse into their secretive research, paints an astonishing picture. Their simulations and early prototypes suggest that a ternary system could be built with 40% fewer components than an equivalent binary one. This leads to smaller, cheaper chips. The patents also claim a staggering 60% reduction in power consumption and a 20% increase in performance. Let those numbers sink in. In an industry where a 5% improvement is considered a major victory, these figures are revolutionary. They represent a generational leap. Still, we have to be cautious. Patents often showcase best-case scenarios and don't always translate directly to mass-produced products. The real, tangible breakthroughs are likely still hidden behind the closed doors of advanced research labs. The cost of reinvention is immense, but the prize for succeeding could be nothing less than leadership in the next era of computing. So, where would this revolution have the biggest impact? The answer lies in the most power-hungry, data-intensive fields of modern technology, artificial intelligence, and the massive data centers that support our cloud-based world. The core promise of ternary logic is its superior information density. Let me explain. A single binary digit, a bit, can represent one of two values 0 or 1. A single ternary digit, a trit, can represent one of three values 1, 0, or 1. This might not sound like a big difference, but it scales exponentially. For example, with 8 bits 1 byte, you can represent 28, or 256 different values. With 8 trits, you can represent 38, or 6,561 different values. You can pack vastly more information into the same number of physical units. This has profound implications. For AI, where computations involve processing immense matrices of numbers, this higher density means you can perform the same task with fewer transistors and fewer operations. This directly translates to higher speeds and, most critically, dramatically lower power consumption. The potential to slash the energy use of AI training and data center operations is perhaps the single most compelling reason to pursue ternary computing today. Furthermore, ternary logic offers a fascinating middle ground between the perfect precision of digital binary computing and the messy, power-efficient world of analog computing. It introduces a level of nuance that binary lacks. But this strength is also a challenge. Creating and maintaining three distinct, stable voltage states in a microscopic transistor is far more difficult than managing just two. The system becomes more susceptible to noise, random electronic fluctuations that could cause 0 to be misread as a 1, for instance. This requires incredible precision in manufacturing and sophisticated error correction systems. The challenge is to achieve this three-state balance reliably and at the scale of billions of transistors on a single chip. For years, the challenge of building a reliable ternary transistor was a major roadblock. Silicon, the workhorse material of the binary age, is very good at being on or off, but it doesn't have a natural middle state. But just as the need for a new logic has become critical, A new class of materials has emerged that seems almost perfectly designed for the job. And this is where nature lends a helping hand. Enter graphene and carbon nanotubes. These are wonder materials, composed of single-atom thick sheets of carbon atoms arranged in a honeycomb lattice. They have extraordinary electronic properties. One of the most exciting is a phenomenon known as negative differential resistance. In simple terms, this means that as you increase the voltage applied to a graphene transistor, its current can increase, then decrease, and then increase again. This up-down-up behavior naturally creates the two thresholds needed for three stable states. It's as if the material wants to be ternary. These materials aren't just a good fit, they are a perfect one. They are incredibly strong, excellent conductors of heat which helps with cooling, and can operate at much higher speeds than silicon. Their inherent atomic structure makes them ideal for building the fast, energy-efficient, and stable ternary systems that were once only a dream. The research is no longer just theoretical. Experimental chips built using carbon nanotube transistors have already demonstrated the very same leaps in efficiency that Huawei's patents promised. One study showed that a ternary nanotube processor performing a specific AI task used 45% less chip area and consumed 30% less energy than the most advanced binary chip designed for the same task. This isn't just an incremental improvement. This is a leap, a fundamental shift in what's possible, all because we found the right material to unlock the power of a 70-year-old idea. So, we stand at a fascinating crossroads in the history of technology. The ghost of Brusensov's Setun is back, no longer a forgotten relic, but a potential blueprint for the future. Will ternary computing replace binary entirely? Probably not, and it doesn't have to. The binary ecosystem is too vast, too deeply embedded in our world to simply disappear. It's more likely that we are heading towards a hybrid future. Our general-purpose devices, like laptops and smartphones, might remain predominantly binary for years to come, but in the specialized, high-performance arenas where efficiency is paramount in the massive brains of AI data centers, in supercomputers modeling climate change, in energy-critical systems for space exploration or medicine, ternary computing could become the new gold standard. But the real revolution here isn't just about transistors and logic gates. It's about the lesson embedded in this incredible story. It's about daring to think beyond either or. For 70 years, our digital world has been built on a foundation of absolutes, on or off, true or false, yes or no. But life, we know, is rarely that simple. Life is filled with nuance, with compromise, with the gray areas in between. The story of ternary computing is a powerful metaphor for the importance of embracing that complexity. It's a reminder that the most elegant solutions are often found not at the extremes, but in the balanced middle. Just as Nikolai Brusensov, in an environment of scarcity, had the courage to question the very foundation of computing, we too can find profound breakthroughs by questioning the binary assumptions in our own lives. We often fall into the trap of binary thinking. Success or failure, right or wrong, friend or enemy. We force ourselves into one of two boxes, when very often, the most creative, compassionate, and effective path, the third state, is waiting to be discovered. The next great leap in technology, and perhaps in our own personal growth, may come from exploring the path that everyone else has overlooked, from having the courage to try the idea that seems too different, too radical. From daring to see the color in a world that everyone else insists is only black and white. So let me ask you, where in your life are you stuck in binary thinking? What is the third option, the middle path, that you haven't considered yet? Thank you so much for joining me on this journey into the past, present, and future of computing. I hope it's given you something to think about, not just about the technology in your hands, but about the way we all think. If you enjoyed this story and want to explore more ideas that challenge the way we see the world, please consider subscribing to the channel. Your support makes all of this possible. Until next time.